The world of AAA game development has been going through rough times for the past 10 years. Long development cycles and poorly optimized games have pushed many gamers to call out games made with Unreal Engine 5 UE slop or AAA trash. But while more and more studios adopted a third-party game engine, one studio quietly perfected an in-house architectural masterpiece. In 2015, Hideo Kojima walked out of Konami with nothing but a vision. When he landed at Guerrilla Games in Amsterdam, they handed him a literal wooden box containing a USB stick with their entire source code. No contracts, no corporate red tape. He called it Decima. But here's an interesting fact. Decima was not built for open worlds initially. It was first designed for the Killzone franchise, a linear, corridor first-person shooter type of games. An engine built for narrow corridors lacks the streaming buffers, the memory heap layout, and the asset pipelines required to render huge distances of open terrain. Guerrilla didn't just patch the code. They re-engineered how a game engine communicates with hardware, treating memory not as a static pool, but as a continuous streaming pipeline. How did they do it? By rewriting the rules of visibility and asset compilation. According to internal Guerrilla and Kojima Productions development papers, Decima bypasses the traditional software bottlenecks that plague modern releases by compiling visual node-based artist pipelines directly into native C++ code at runtime, while cutting the world into a strict 1-meter integer grid. Today, we are going inside the actual GDC and SIGGRAPH documentation to decode the genius engineering of Decima. We'll look at the data streaming architecture that handles millions of assets without trouble, the radical Nubis volumetric system that completely changed real-time skies, and how its unique visibility matrix gives environment artists a level of procedural power that leaves most other modern game engines scrambling to catch up. Welcome to the architecture of Decima. First, a brief bit of history on the Decima engine. The origins of the game engine can be dated to 1998-ish. In 2013, Guerrilla Games were working on a PlayStation 4 launch title called Killzone Shadowfall, a linear first-person shooter experience that was developed using what the devs simply called the engine. The engine excelled at high-fidelity static geometry, narrow-view frustums, or the field of view of the camera, because most of the game was set in tight corridors and heavily scripted sequences. When the decision was made to move on to a massive open-world RPG like Horizon Zero Dawn, many devs thought transforming this game engine was nearly impossible. An engine built for tight areas and scripted events is hardly the best option to handle vast streaming worlds and complex enemy AI. While working on Horizon Zero Dawn, the studio handed a modified version of the engine to Supermassive Games that were working on Until Dawn. This version was using a modified Havoc physics that also powered Horizon Zero Dawn. Later on, for Horizon Forbidden West, the open-source physics engine Jolt Physics was integrated in Guerrilla Games' game engine. The name Decima came from Hideo Kojima. In 2016, he visited Guerrilla Games Studio, and in a now legendary gesture, Guerrilla presented the source code of their engine in a wooden box. While no contracts had been signed, which is not a common thing in this industry, Kojima named the engine Decima in honor of an island called Decima in Nagasaki, Japan, that served as the sole Dutch trading post during the 17th century, making it a great symbol of the bridge between the Dutch team at Guerrilla Games and the Japanese team at Kojima Productions. And the rest is history, as they say. The system that the engine was using for the Killzone games was based on a tree of mesh resources. There were LOD meshes which select between different branches and multi-meshes to place branches relative to the root. And at the leaves, there were static meshes containing the geometry. Instances of mesh resources were placed in the world as drawable objects. The leaf nodes of this tree contain drawable setups, which are what is fed to the renderer. Each is a chunk of geometry with the shaders and state needed to render it. They isolate the renderer from the rest of the content. queries are CPU jobs, which are part of the general rendering job graph. There was a flexible job architecture on the CPU. Most code and all rendering code runs in jobs. This system would not work for the world size of Horizon Zero Dawn. The devs needed to reduce the complexity of the KD tree because it would be rebuilt often as content streamed, and they needed to run fewer mesh instance tree queries as they were expensive. Also, the Scene API was aimed at few large objects, and Horizon's world would rely on a vast number of tiny objects. So what Guerrilla Games devs did was to build a single-purpose system to ease the load on the existing multi-purpose system. The static scene handles just static geometry. They could use the existing system to handle the remaining dynamic geometry and run the jobs in parallel. They also aimed to use the PS4's asynchronous compute since they thought that it would better handle the amount of content and would be relatively easy to synchronize with the CPU. They had to create a spatial structure to call all this data. They split the world into static tiles, which are either true spatial tiles or, in other cases, things like settlements or encounters. These were defined by the streaming system and were created immutable and couldn't be updated to simplify things. A tile is mostly flat buffers of GPU data with a list of clusters used on the CPU for first pass culling. To save space, all the elements other than the query instance are hashed and stored exactly once per tile, with the instances looking them up by index. The data is mostly indices. Some filters bits to indicate visual meshes and different types of shadow caster, and the parent and child LOD ranges for the leaf the instance is in. The game world uses a high precision coordinate system to avoid problems caused by floating point precision loss away from origin, and the renderer works in a floating space which follows the camera. We pass in a high precision object transform based on a 1 meter integer grid, and the query shader subtracts the snapped camera origin and outputs floating space transforms to the renderer. The query setup has accurate local bounding information which is used for frustum calling. The streaming system loads and unloads objects on a background thread, since loading can happen over several frames. The static scene receives sets of added and removed objects, with the adds and removes guaranteed to match up so there won't be any partial unloads. Generally, a group of added objects creates a single static tile. But if the tile would have a lot of query instances, more than 24,000, it gets split up. Also, if it would have very few, like under 1,000, it gets added to a special orphan tile. All the heavy lifting, spatial partitioning, memory allocation, etc., happens on the streaming thread. The main thread just has to make tiles active when they're available. A spatial partition is needed to break up the data. First, the static tiles provide the first level since they're generally coherent already, and a partial spatial partition is created within each tile to define clusters. Also, the devs generate a sort key or each query instance using filter bits, maximum LOD range, and Morton number. The filter allows to quickly discard clusters that aren't relevant to a query, and the LOD range does a similar thing for dense areas of content. The Morton numbers give a degree of spatial coherence. After sorting, the changes are used in sort keys to define clusters, again with a minimum size of 4,000 instances to help with load balancing. Each cluster is a potential compute job. Morton numbers, introduced by Guy McDonald Morton, are a way of mapping between n-dimensional coordinates and a one-dimensional value. In 3D, this is like building an octree, and the increasing Morton numbers follow a z-order curve like the other one in the picture. They're pretty easy to compute with bit tricks, and if the Morton numbers are close together, then the positions are generally close together too, so these are useful for quick and dirty spatial structuring. There are better but more expensive curves available, such as the Hilbert curve. The tile and cluster hierarchy is used to skip as many clusters as possible and dispatch one compute job for each visible cluster. Then, the CPU job waits for compute to finish. This is nice and simple and avoids having the CPU job scheduler synchronize mixed job types. The GPU jobs that is dispatched uses a single Uber shader which is specialized into a handful of compile time variants. These all have reduced instruction and register count versus the generic shader, which helps the GPU compute units run more wavefronts at a time. The generic shader is only used when query options are switched from their default settings, which is a debug-only thing. The shader is pretty long, around 1,500 instructions in most cases. With the studio working on increasingly larger games, the need for new tools became a necessity. Guerrilla Games was using an intermediary storage format called Cortex that was used for almost all the data except for textures and for audio. They had a custom Maya plugin that allowed the artists to work on the assets in Maya and then export them in Cortex, and the plugin was using the Decima renderer in the viewport so the devs could see exactly how things would look in-game. It was not running the entire game loop and would not render many game systems. There was also the State Machine Editor, or SMED, which was generating Lua script that was mainly used for level scripting in the Killzone games. So the main issue with these tools was that they were not communicating to each other, and the devs had to go back and forth between those to get things done. The team implemented the debug UI probably out of the frustration that the pipeline was causing to many members of the team, which was rolled out during the production of Killzone Shadowfall. That debug includes an in-game GPU profiler, and the coolest feature is an X-ray view that users can move across the screen and isolate every buffer. After a lot of work, here is a quite recent version of the Decima Engine level editor and the visual script editor. And finally, the conversation editor, which is something needed for a team working on a long RPG game with lots of dialogue. The next big decision that was made early in production was to replace the Maya plugin by a 3D editor that could run the full game. They decided to develop the 3D editor as if the game was running in separate process, so no data was to be shared between the editor and the game. Now let's take a look at what this tool allowed the devs to do. While playing the game, they could stop the action and start modifying the foliage to create an encounter. They could remove and add trees to make the area more suitable for what they had in mind. Sculpting the terrain was also just as easy. After that, the encounter designer could just as easily create an encounter and bring it into the world by choosing the enemies from the asset browser. Other world elements, such as a huge rock, can be drag and dropped in the environment. Save and test it right away with the full game features. Here we can see their tool to create and modify roads in the 3D editor. As the road segments are moved, it adjusts the surrounding foliage and environment assets. Pretty sweet. Another great tool developed by the team is the conversation generator. Let's watch a short conversation between Aloy and an NPC.
He gave them the best work he'd ever do. And look at it now.
They defaced it because they hated what it stood for.
They defaced a thing slaves like him lived and died for. Slaves they've already forgotten. Short-sighted bastards, the lot.
By simply typing text, the cutscene or the animations, gestures, and the camera cuts were generated by the tools. No designer had to edit all that. They had a robo voice and lip sync animations available for mock-up dialogues. Before committing to sending to the voice actors, the writers could get a good sense of how it would turn out. Now that's a brilliant tool for Horizon Zero Dawn. When I played this game in 2017, I couldn't believe the level of polish that went into every dialogue and interactions I had with NPCs, from very important ones to those who had much less impact on the story. They also had a world map viewer that allowed them to see the encounters and all sorts of information, but this tool came about pretty late in production, so it was not used very heavily on Horizon Zero Dawn. I'm happy to introduce a new partner of the channel, Bundle Foundry. You can get several tutorials for a very good price here. The current bundle that is still available is called Become a 3D Artist Mega Tutorial Bundle. Several bundles just launched. You want to check this out. Check out the price also. This is great value. This is a great opportunity to level up your skills at a great price. Links to the bundles will be in the description. The visual programming system of the engine has been expanded to topics of animation, gameplay, audio, shaders, cinematics, effects, UI, and more. The first system started with Lua scripts during the production of Killzone 1 in 2004. It was only used for encounter scripts, menu, and player spawning logic. At some point, the Lua scripts started to become tied together in more complex setups using the State Machine editor. They had a tool called Modo for audio designers, which evolved into the current tool that is used nowadays. Let's now look into the shader graphs. The engine had a plugin that allowed the Maya shader graph to be translated in the Decima Engine, but the devs wanted more integration and better previewing with real game data. The programmers didn't want pixel vertex shading passes exposed to user. So the surface graph is analyzed and split into vertex and pixel graphs, intelligently put some logic on either side depending on GPU interpolar capabilities. Those are turned into intermediate representation as usual by framework. That is turned into generated code by shader backend. On release, all character, building block, and vegetation shaders were shader graphs. The artist could author and preview shaders in Decima itself instead of third-party renderer, which means that it could load real-game data and supported standard Decima live tweaking and hot reloading of assets. Regarding lighting, Decima is known for achieving top-tier results through brilliant optimization. While the engine began as a non-ray tracing powerhouse, newer versions, like those in Death Stranding 2 on the beach, have begun incorporating ray tracing features. However, the engine's signature remains its ability to achieve photorealism through advanced global illumination and volumetric cloud system known as Nubis that don't require the massive computational tax of full hardware ray tracing. We will take a close look at their wonderful Nubis system later, but first, let's examine one of the advances made in the engine while the team was working on Horizon Zero Dawn. The Decima engine was one of the first game engines to support lighting using area lights. However, it did not support GGX, which is a shading model that is used within PBR pipelines to provide realistic natural-looking specular highlights with bright, sharp centers and soft, extended tails. So the devs set out to upgrade their area light system by adding GGX to their spherical area lights first, but integrating a micro-facet BRDF or bidirectional reflectance distribution function like GGX into an area light is difficult and requires some sort of approximation technique. Some techniques prefer quality over performance and vice versa. For the spherical area lights, the devs opted for the light bending trick described by Brian Karras because it's cheap and had already been used by many other game engines. One problem remained though. This trick can cause some unexpected shapes to emerge, especially at grazing angles. I will skip the long math lecture, but the link to the SIGGRAPH presentation is in the description for those who are interested. I will show a quick overview for now of how the great devs at Guerrilla Games solved this issue. Here is what it looks like in HLSL, the code used for shaders. And this is what it looks like when they add 1 Newton iteration. It does add quite a few instructions, but for a light shader, it's not much. And it's worth it, as we can see here, the result is quite similar to the Karras trick, but much cheaper. Now let's take a look at the hide fog model developed by Kojima Productions. Initially, Decima had a flexible atmospheric scattering system linked with clouds and outdoor lighting, but Kojima Productions requested an atmospheric scattering system optimized for photorealistic rendering. They also needed this system to be artist-friendly so that they could easily tweak the density and the color of the fog in-game. The solution was to combine an analytic hide fog and a pre-computed atmospheric scattering model. Here's an overview. The starting point is the volume rendering equation and the Earth's atmospheric conditions. Those are described by the Rayleigh scattering and the Mie scattering and the participating media with exponentially decreasing air density with altitude. The pre-computed atmospheric scattering model performs numerical integration and stores the in-scattering and transmittance information into the lookup tables. On the other hand, the hide fog model calculates the fog directly when the scene is rendered. This calculation is an analytic solution of the volume rendering equation with assuming the single scattering. This kind of analytic solution is known for the uniform fog model, but they couldn't find a good solution for the hide fog model. So they derived it independently, assuming single scattering and single scale height. The scale height is a parameter to describe how the fog density decreases with altitude. In this approach, they supplied the skylight and the sunlight information from the pre-computed atmospheric scattering model to the hide fog model. Let's look closer at this combination. Assuming there is sunlight, this extraterrestrial sunlight is incident into the Earth and interacts with the air. The pre-computed model generates its multiple scattering information and stores it as the LUT L in scatter, L sun, and L sky. The hide fog model receives the background radiation, the sunlight and the skylight from the pre-computed LUT. A typical pre-computed atmospheric model has an in-scatter and transmittance LUT, but the devs replaced the transmittance LUT with sunlight and skylight LUTs so that the sunlight and skylight information is given directly to the analytic hide fog model. This is an example of the LUT. Now we have the scattering information as 3 LUTs. This is a sample code of the hide fog model. And this is the result. Left is the final result. Next is the background radiation. Next is the background radiation multiplied by the alpha. Note how the transmittance alpha is causing the color of the sunset. Next is the sunlight component, and at the end is the ambient component. When the 3 on the right are summed up, we get the result on the left. This is a sample scene from the Decima Engine. Now is the time to deep dive into one of the greatest features of the Decima Engine, the Nubis system. According to Andrew Schneider, what made Nubis successful was the ways in which they compressed the cloudscapes and added density and lighting details, which are specific to clouds, at render time while fine-tuning a rendering technique known as volumetric ray marching. Their method of ray marching turned compressed cloud models into rendered frames of clouds in between 0.2 and 5 milliseconds, depending on if we viewed them from afar or if we flew through them. In a ray march, once you know that your pixel contains clouds, the idea is to step along the part of the ray that intersects the top and bottom of the cloud layer. And at each step that contains cloud, you sample density and you sample lighting, which requires a secondary and quite expensive ray march toward the light, and then you integrate these data with the results of the previous step in a way that produces color and opacity data for each pixel. This is repeated until we reach full opacity, and this is also done for every pixel to produce a full render. Starting at the heart of the ray march, the density sampler. We'll be focusing on 2 of the cloud rendering methods here, as both methods directly inform their approach to voxel-based clouds. The first is the vertical profile method, which was used for high-altitude tropospheric clouds that the player could not reach, and the second is the envelope method, which were used for orographic clouds that the player can fly through. 2D data fields that they call Nubis data fields, or NDFs, contain instructions that the cloud rendering compute shader uses to decompress 3D clouds from authored 2D data. These 2D data fields were mapped over a 16-kilometer area of the world and sampled at render time to get the data needed to construct 3D cloudscapes. During the ray march, when sampling density, both methods constructed a high-resolution 3D volume, as seen here, from a low-resolution dimensional profile, as seen here. Even though these may look similar, the way that the dimensional profile was constructed differed per model. In the case of the vertical profile method, they started with 5 2D NDFs. Cloud min and max height defined the vertical range for the cloud. Top type and bottom type were used to sample vertical profile lookup textures, and the results were multiplied to create what they call the vertical profile. Then, they scaled this vertical profile by the cloud coverage data to control where clouds formed. In the case of the envelope profile method, they started with 4 2D NFDs. The min-max height were used to define an envelope in which clouds could be rendered. The dimensional profile was the product of 3 gradients: a top gradient that increased in value pointing down, a bottom gradient that increased in value going up, and an edge gradient that increased in value going in from the sides. They used 3D noise to erode the dimensional profile, then up-res it into the detailed results you see here. They developed what they call Perlin-Worley noise to simulate a mix of wispy and billowy details in clouds, and they use Worley noise to simulate the billowy details seen in clouds. These were combined in various ways per model to create what they called noise composites for potential wispy and billowy details at the sample position. Then they blended from wispy to billowy noise composites using the type data at the sample position. The erosion was modeled as the subtraction of the inverse of the dimensional profile from the noise composite. Pseudo-motion was simulated for both models by animating the noise in the wind direction. After sampling density, they sample light energy. Both methods define light energy as the sum of 3 components: direct scattering, which represents all of the light energy coming from the sun; ambient scattering, which represents the light energy coming from the sky and neighboring clouds; and secondary scattering, which represents the light energy from sources like lightning. They define direct scattering at a given sample point in a cloud as a function of 3 probabilities: transmittance, scattering phase, and multiple scattering. Transmittance is a measure of the amount of light at a given depth in an optical medium. The graph indicates how the intensity of light decreases as more of it is absorbed over depth in the cloud. In order to gather this depth, you must conduct a second and very expensive light ray march toward the light. Scattering phase is a measure of how much of the energy that reached the sample position will scatter towards our eyes, given the view vector and light vector. Light scatters in a cloud as it refracts through tiny water droplets or ice. In clouds, light has a tendency to scatter more along the original path, so they use several Heine-Greenstein phase functions to produce an effect that is art-directable and somewhat physically based. Multiple scattering describes light that scatters in to the view vector after refracting around from multiple encounters with water molecules. They use their dimensional profile as the basis of a probability field to describe where in-scattering happens more frequently, because the deeper you are in a cloud, the more potential there is that photons have scattered around from their original path. They attenuate this field using another Beer-Lambert attenuation curve, as the multiple scattered light itself is eventually absorbed the more it scatters. They also attenuate this over height to account for the fact that less light scatters into the cloud from below. Finally, they scale this by a phase function to ensure that it too is directional. Here is what a cloud looks like without multiple scattering approximation, and then with this approximation method. To approximate the effect of ambient light entering the cloud from all around without ray marching too many light sources, they once again model this geometrically as a probability field. The majority of light comes from above and around and penetrates just the surface of the cloud. The dimensional profile already provided the gradient from the outsides of the cloud to the inside. They used the inverse of the dimensional profile to create a gradient representing the probability that light will reach a given point inside the cloud and then scatter to our eyes. Here is what a cloud looks like with just this ambient component, then with just direct light energy, and with both direct and ambient light energy. Now secondary light energies. Normally, for any light source that is positioned inside a volumetric effect, you need to do an expensive second light ray march for each sample taken. For those keeping track, that would mean 3 ray marches. Not an ideal approach. Once again, they looked at lighting as a geometric probability problem. They modeled the volume of light that would approximate the light energy present at each sample taken around the light source in the primary ray march. Here is what this looked like in our superstorm from Horizon Forbidden West. The next step is to determine the step size for the ray march so that the next sample can be placed along the ray. The vertical profile method employed an adaptative step size, where the size of the steps increased over the distance from the camera. This resulted in fewer samples farther from camera, where less precision was needed. Times range from half a millisecond for cases like this, where you're looking at partial sky, to 2.2 milliseconds in cases with full sky visibility. However, to support flight through clouds created with the envelope method, which are almost all near camera and required a lot of samples close by, they had to get a bit creative in order to avoid placing a lot of samples in empty space. They combined two methods called cone step mapping and distance step mapping so that they could place samples as efficiently as possible while using only height data. When ray marching, they did an intersection test between the ray and cones generated from surface intersections to determine the largest step they can take before hitting any clouds. The distance step mapping was used to make sure that they did not take too many samples for areas outside of these cones and outside of clouds. As they began to sample inside the envelope, they will start to take smaller ray march steps and sample the actual cloud density. In this image, you can see that the samples, as indicated by the red dots, are focused around clouds and not as frequent in empty space, which is a better distribution. But how much could this save? Here is the cost before, 4.2 milliseconds, and a more comfortable 1.3 milliseconds after. There is much more to this breakdown of the Nubis system, but I will let you read on your own as it is a very long presentation, and it's worth going through all of it, but I cannot make the video run for hours. Now we have to mention the foliage of Horizon Zero Dawn. As the first open world game made with Decima, one of the things that impressed me the most was the foliage in general. In every different biome, the grass, the plants and the trees were so impressive, especially in 2017. I remember spending way too much time just turning around trees or hugging walls that had vines attached perfectly, and I was amazed by their tech. Today we will look into some of the tricks they pulled to reach that level of realism. We can see that everything is well optimized regarding the meshes, but they were using what they call low and high standards, which means that the LOD3 had no animated vertex program and no normal map in that version of the shader. One very cool feature is the camera-based tilting, which helped not make the grass look like a bunch of cards, which they actually are. Okay, so now we will get the secret of the sauce, so to speak. Let's look at their shading setup. So they render all their alpha-tested meshes in 2 passes. First, in a depth-only pass, they do the alpha test. Rendering this pass first gives them all the depth information, after which they only have to do a depth compare when rendering the geometry pass without an alpha test. This is brilliant because alpha test is very expensive, and by using this method, they have a very cheap depth-only shader. Let's take a look at a frame of the game to see what it means for rendering times on the GPU. Here is the GPU profiler in-game. The depth prime pass is close to 10% and the geometry is around 11.5%, for a total of roughly 21%. And now let's see the result without rendering the depth-only pass. 45%, more than double. So that's one of the main reasons why Horizon Zero Dawn has so much foliage everywhere and it runs very smoothly. Let's now take a look at the other buffers. So the Decima engine uses deferred shading, and here are the textures that are supplied to the shader. Note that grass never has an AO texture. And here we can see how they pack the channels of a typical setup of a vegetation texture. Here's another neat trick that they used. Because they were relying heavily on cards with low amount of triangles, they found that flipping the normals could be very helpful to hide the card-like nature of these assets. They adjusted the normals of the vertices and took the absolute value of the view space normal to avoid rendering normals facing away from the camera. So let's compare in the G buffer the normal vertex normals and their custom flipped normals. And here's the assets viewed in-game. It's an artistic choice that is breaking lighting and translucency, so they did not use it on every asset, but I think it's brilliant and looks very good. Here's the albedo. All the vegetation in Horizon Zero Dawn is colorized. They used a texture array that stored 64 of what they called ecotope of colorized textures of 128 by 8 pixels. The textures also hold colorization of rocks, terrain, dust, and lichen. The location of the asset in the world dictates which texture to sample. Different types of world data are captured in one grayscale texture, and the artists can choose between 8 bands to colorize the assets. To make things easier, they averaged out the color of the albedo textures to a mid-gray value, and they all have a mask for the parts that will not be colorized. They overlaid the colorized value on top of the albedo texture through the mask texture using an illuminate function. The resulting color is the background color mixed with the foreground color, brighter where the foreground is bright and darker where the foreground is dark. And this is the result. So this is why that vegetation looks so good and feels real. There is an incredible attention to details and to how light affects the color of the leaves. Now onto the roughness and reflectance texture, which are derived from a combination of other textures. The ambient occlusion baked in the vertex alpha and a variable fixed at 4% dielectric. For the roughness, they wanted to give more control to the artists, so they added a level of the translucency texture on top to make it easy to differentiate the roughness between leaves and bark. For grass, it's mostly using the translucency texture. For translucency, the surface thickness, pre-computed AO, and a boost of the amount of scattered light, which breaks away from physical correctness but was in line with the surreal look of the game. So there we have it. There are so many intriguing decisions that were made by the team that it's not surprising that the foliage made in Decima looks unique and quite ahead of most other game engines. There is more information available on this topic. I will provide the link to the documentation in the description. If you're learning from these videos but are still struggling to put everything together into a full environment, that's exactly why I built my full course. You'll build the entire scene step by step in real time, understanding composition, scale, materials, and lighting, so you can apply the same process to your own worlds. These environments were created by students using the same workflow you will learn here. It's designed for artists who already know the basics and want to create a professional portfolio work, not just isolated studies. This isn't about learning tools, it's about learning how professionals build environments. If that's where you're trying to get to, you can check the link in the description. Kojima Productions use photogrammetry in Death Stranding to capture Iceland's raw geology. The developers sample real-world data and use micro-topology displacement maps to create highly detailed, responsive landscapes that blend materials based on environmental factors. Instead of relying on a flat polygon with a texture, Decima's terrain shaders read the high-frequency displacement maps generated from the Iceland scans. These displacement maps physically offset the vertices of the mesh at render time, adding micro-shadows and true 3D topography to the stones and gravel on a pixel-by-pixel basis. Rather than painting static textures, the terrain system builds a material graph combining different surface types: wet mud, jagged stones, fine gravel. The shaders evaluate the geometry's normal vector. If the angle of the surface is steep, gravity and slope-based logic tell the shader to reduce gravel accumulation and expose a jagged volcanic rock. The engine's environmental systems track moisture, like from rain or timefall. This influences the physically based rendering values, changing the roughness and creating specular reflections that make mud appear wet and reflective. The Decima Engine achieves its acclaimed visual and performance stability primarily through its internal profiling, runtime rendering analysis, and memory management suites. Instead of exporting data to an external tool to track down frame dips, developers can open diagnostic overlays inside the live environment. This allows them to identify how specific assets affect the rendering pipeline on the fly. A feature Chief Technology Officer Akio Sakamoto highlights as a massive competitive advantage. He also said that building and modifying these internal tools allowed them to accomplish feats of optimization that would be incredibly difficult to execute in a standardized engine environment. Managing memory is critical for titles boasting complex physics and high poly counts, such as the 25 million polygon landscapes seen in Death Stranding 2. Decima's memory tracking allows the studio to monitor fragmentation in real time. If a massive sequence triggers a memory spike, developers can trace it to the exact code thread and optimize the system to maintain a locked 60 frames per second. While a growing portion of the industry consolidated around general-purpose third-party engines, Guerrilla Games and Kojima Productions chose a different path. By engineering specialized pipelines like the Nubis volumetric cloud matrix, the mesh resource tree for absolute spatial visibility, and a compiler that turns artist nodes directly into uncompromised C++ native code, Decima stands as a masterclass in proprietary design. It is living proof that when you build an engine tailored specifically to hardware execution layers, you don't have to choose between boundary-pushing photorealism and a locked 60 frames per second. You can have both. As we head into a new generation of game tech defined by massive data streaming and procedural generation, Decima isn't just keeping up with the industry, it's dictating the pace. I do have a free portfolio checklist that can help you figure out what is important to employers and might help you save some time on your way to your first or second job in the industry. The link is in the description. And a quick thank you to the members supporting the channel. Your support helps make these videos possible.